All right, welcome to week 3, and I'm really excited for this because this is where we really start to do some real regression. And I absolutely love this subject. I love this topic. I love teaching it. I love making it easier for people. I love empowering people with it. So we're actually going to do some cool stuff in this video and get you going with doing things in R in the other videos and starting to interpret things. So this is probably the most foundational information, and everything builds from here. So we'll go through the key stuff from chapter 1. You're going to get a lot of my own details on it because I don't think the book is as good as it could be in covering this material. And there's some other topics in chapter 1 that it's good to look at now, but you're not going to need to worry too much about it until later. So let's dig into what we're doing here now with actual regression. So let me just keep it generic at the moment for, say, we have some response variable y and some explanatory variable x. And as we make some examples with it, in our data, we've been having house price as our response variable and house size, square feet, as our explanatory variable. And you're going to be working a lot with these on your first homework and on your second homework. So we'll refer to these variables in these examples here. So remember that the whole point of why we want to do this is we want to explain price. We want to explain a general response variable, perhaps y. And we want to find out if there's another variable, another factor, that explains why prices of houses are changing, why some generic response variable is changing. So the way we conceptualize regression is we say, well, let's just look at a scatter plot of the data. Let's just see how they might relate to one another. And you started to do this last week by calculating a correlation coefficient and looking at a scatter plot. So I'm just going to make up a graph here, and I'm just going to make up generic x and y. And I'm going to put on some generic data here. Just making it up. Something like this. It's kind of a lot of points. Just take out some of these overlapped ones. Okay. So this is fake data. Let me fill some of these in here so you can see a little bit better. And we see that there's some relationship here between x and y. And it looks like it could be linear. So what linear regression does is it says, I want to fit a straight line through these points. That is the best line that I can fit through these points. Now, what does the best line mean? Well, let me draw on, for example, what the best line might look like. You'd think that it might go through our sense of what the middle of these points are. So maybe something like this. What linear regression does is it fits a line that minimizes the distance between the line and each of these dots of our data. In a generic sense, that's all linear regression is. It's saying, give me the line that gets close to these data, that gets close to our dots as much as possible. Make this distance between the dots in my line as small as possible. So we'll talk more about that in a second, but let me just throw out some formal notation here. The base notation. So when we do linear regression, we're working with the idea of a line. Remember back to your basic algebra. A line is represented by, maybe you recall the idea of y equals mx plus b. Maybe you recall that from your general algebra, where m was the slope and b was the intercept. That's the convention we're going to be using, but we're going to write it a different way. The way we write our theoretical model is in the form y equals beta 0 plus beta 1 x plus this thing called epsilon. What this is the theoretical model that is supposed to represent the population and the true relationship that is out there in the universe. This is the theoretical model we start from. Its components consist of the response variable, then something called beta 0, which stands for an intercept, just like a regular algebraic intercept. And we'll connect that to this in a second. Followed by beta 1 times x. Well, x is our explanatory variable, and beta 1 is just the slope that relates x and y. Beta 1 is the slope that relates our explanatory variable to our response variable. And when we write out our theoretical model, there's always some error in the universe that we just can't account for when we make a model, theoretically even. And so we throw on this error term on the end. But again, this is what we start from. This is, in a sense, what our initial idea is before we've even run anything. And this is how we write it every single time. In the case of price in square feet, we would just put price in place of y and square feet in place of x. And then we have the theoretical model for our price in square feet situation. Great. So let's say we run a regression, and I'll show you a little bit more of what R does when we actually do that in a second. Let's say we run a regression. We get this line, this best line, to represent the relationship between x and y. So how does that connect to what we wrote up here? Well, this has numbers to it. This line has an intercept. It has an intercept with where it hits the y-axis. This corresponds to beta 0. And I put a little hat on it to indicate that this is coming from the actual regression line. We don't know what the true theoretical intercept and slope coefficients are out in the universe. We don't know that because that's why we're doing statistics and modeling. So I put a little hat to indicate this is the estimated intercept. And because it's a line, I can put a slope on, I can indicate a slope on here with beta 1 and a little hat. And to represent this idea of a rise over a run. So this line has slope beta 1 all along here. So all it is, the estimated line that we work with, is this theoretical model, but now with little hats on things. Not everything, but I put a hat on my response variable because now I'm predicting it. I'm using my estimated model to give me predictions of my data, to give me predictions of my y value. So I put a little hat on it to say, this is my estimated y value at a given x. And I have an estimated intercept and an estimated slope that all come from this line. So for example, I could put in some fake numbers and say, let's say that this is square feet and price, and let's say that my intercept here is, say, 100,000. And let's say that this line had a slope of 150. What this means is that I can write an estimated model like this. Prediction y hat is equal to my estimated intercept, which is 100,000. Plus the value for the slope of my line, which is 150, times my explanatory variable, x. But whenever we know exactly the variables you're working with, I want you to put in the actual name of the variables we are working with. So price and square feet. And that's it. This is a fake data, made-up example of how I get a line that I fit in here with our regression in R, and then how I write it down below. I have my response variable with a little hat on it, again, because I'm predicting it, I'm estimating it with a model. I have my intercept for my line, my y-intercept, and then I have a slope that describes the relationship between square feet and price. So there's some important things here. What does this 100,000 mean? What this $100,000 means is that it is the value, the predicted price, the predicted average price when square feet is 0. That's our usual interpretation of an intercept. Go on my x-axis, go all the way to 0, and where does my line cross my y-axis? So what it's saying in this case is at square feet equal to 0, I predict an average price for my house of $100,000. The very important thing about the intercept is that we often don't interpret it because it just doesn't make sense. So here's the trick. Would we ever have a house that's at 0 square feet? No, that makes no sense at all. So we don't interpret this 100,000 on its own. We also do not interpret any, we don't have 0 in the data set, is what I'm trying to say. So we wouldn't even interpret it anyway. You never interpret a model for stuff that's outside of your range of data. What about this 150? Well, it's a slope. Remember that a slope is a unit change in x corresponding to a slope change in y. So it's a run and it's a rise. It's a run and it's a rise. It's a change in x, it's a change in y. It's a change in x, it's a change in y, consistently. So how we interpret this is to say a 1 unit increase in square feet is associated with an average increase in price of $150. Again, a 1 unit increase in square feet corresponds to or is associated with an average increase in price of a house of $150. Again, it's change in x corresponding to a change in y. This describes our relationship between what we care about, the price of a house, and what we're trying to use to explain it, the square feet. And I go through this in the help guide for interpreting our output, so you have this in typed out words as well. But that's all this is. So this is all good, but I want to help you understand how we even get this line in the first place and what more we can say about it and some other things that have come up in chapter 1. So let me erase this for now. And don't want to erase the data. So let me erase these little marks here. Sorry for the dead air. I don't have time to really edit anything out. So you can just feel free to fast forward until I'm done erasing. Okay. I'll do this over here. So when R puts this line of best fit among these data, what it's doing is it is taking each value of y I'll just write yi, some value of y, and then it's looking at the distance between the point and the line, which I will indicate this. And it is taking this distance, squaring it, and doing that for every single one of these points, and making that distance as small as possible. So again, what it's doing is it's taking each y, comparing it to where it would be on the line. So a predicted value of y, y hat, and squaring that, each one of these, so it's getting this distance, and this distance, and this distance, and this distance. It's taking the distance between all these things, taking the difference, squaring it, and then it's adding it all together and saying, I want this distance, the square distance between my data and my line to be as small as possible. And that's all regression does. And this is called ordinary least squares. or OLS. Again, it's just saying I want a line that minimizes the square distance of my data and my line. And you may be asking yourself, okay, yeah, I can find a difference between a line and a data point, a vertical distance, but why are we squaring it? Well, we're squaring it because if you put a line right down the middle of these points, these distances up here will perfectly balance out these distances down here. So the amount of distance above the line with these points with respect to the line will be completely equal to the distance of these points below the line. And if you add it all up, so if you took all these distances and added them up, it would equal 0. And that's not very helpful for us, because that doesn't help us to say how well our model is doing or not. So that's why we have to square this. Because then every single line that we would put in the middle of data points would give us a distance equal to 0. And an average distance over these things equal to 0. And that's not very helpful. So we square them, excuse me, and say, I want this as small as possible. And that's how it picks the line. Now, obviously, the line sometimes gets it pretty close. Other times, the line is really far off. I got this observation up here. So I can quantify that. In fact, we've already started doing that. So let's get some terminology out of the way. A predicted value is simply whatever point my line gives me for a given x. So we've already, in a sense, seen what a predicted value might look like. So if I just write out this generic model, and let's pretend that these numbers are the same as before, 100,000 plus 150 times x. For each x I plug in here, it's going to give me a value for y hat that's directly on this line. So if I want the predicted value of, say, x at 10, to just make this up, then I just plug 10 into my estimated model. And I get 100,000 plus 150 times 10, which is 100,000 plus 1,500, which equals $101,500. So if I, for example, I took data and I definitely had houses that were somehow 10 square feet in size, which seems unlikely, I could say, great, what's my predicted average price for a house of 10 square feet in size? I just plug it into my estimated model, and I get a prediction of 101,500. And let's just say that that was somewhere right here. Great, so that's my predicted value. but how close is it to the actual observation? So again, the predicted values are all on this line here, but let's say I actually have a house that's 10 square feet in size, and let's say the actual value the actual price for a house at 10 square feet is equal to 110,000. So again, I've got a predicted price of $101,500. But let's say I have an actual price that the actual data point is at $110,000. So I can calculate something now called a residual. The residual is just the actual value minus the predicted value. And in this case, the actual value is 110,000. The predicted value is 101,500. And so I get a residual of, that should be $8,500. So my model in predicting how much a house would cost that's 10 square feet in size was off by $8,500. When the residual is positive, we say the model under-predicted, or I should say, yes, under-predicted, because we see that it predicted something that was smaller than what the actual observation was. The model can also sort of over-predict things. You can get negative residuals. So if any of your points, for all points, they're above the line, we get a negative residual. For all points that are below the line, we get a positive residual. Because this distance, again, is the residual y minus y hat. And you're starting to see this connection that what our line is doing when we run a regression is saying, I want the sum of my squared residuals to be as small as possible, which makes sense. A residual is bad. A residual is saying how well our model, how much our model missed. So we want our model to not miss. So we want the sum of these square deviations as small as possible. So sort of in review with all this, we have data, we fit a line to it, and then we can say, great, this line is just filled with, is just a series of predicted values for price given different square feet. And I can then take those predicted values and compare them to the actual values, the actual prices, and get a residual. And I get a residual for each one of my observations. I can square it, I can add it up, and that is the thing I want to make as small as possible. There's two other big points to make before we talk about assumptions, and then that should be it for this. One important thing I want to point out is how we write our equation. So if you remember, we were writing this as, or estimated as, the estimated price, our intercept, our slope, and our explanatory variable square feet. Remember, we put the hat on this because we're estimating price. But here's where it's really cool. We can add in a term if we want on the end here for the residual. When we add the residual into our estimated model, we get the actual observed price back from our data. Because the model, again, is this line. And then if I add in the residual, it takes me to the actual price. So you can think about our estimated model in two ways. You can think about it as giving me a value on the line. And so I use a little hat to show that. Or you can think of it as starting on my line here, and then adding in whatever the residual is to get me back to the actual price. This is how I would like you to write your estimated equations. I'd like you to do the hat on the response variable. Okay. Next thing is, there's a very important word I want you to use a lot, and it's the word average. This line is predicting the average price at a given X value. So our model predicts averages our slope coefficient is about average change. So when you're writing your answers to things, and you'll see my written answers to things so that you get the full clarification on it, I want you to be talking about in terms of averages. I will dock points if you don't talk about things in terms of averages. So if I predict that price before of $100 and $1,500, that's the average predicted price at 10 square feet from that previous example. 150 is the average change in price for a 1 unit change in square feet. The linear regression line is just about average change. And you'll see that more in week 4 when we get into what it's actually predicting. But it's actually just doing averages. And so that's how I want you to phrase things. Great. So lastly, we need to talk about assumptions. And you're going to be doing a lot of work with assumptions. And assumptions are a key thing of this whole process. Oh, before I get to that, excuse me. One important idea that I totally forgot about. It's really huge. Sorry for the detour. So remember how I was telling you that we can get our average deviations from we can get our deviations of each dot from the line, and we call those residuals, and we can add them up like we do here. So I get my residual, I square it, I add it all up. What I can do is I can divide by n minus 2, and I can take then the square root of all of that. You will never have to do this by hand. You'll never have to calculate this thing. All I'm saying is that you can take these residuals, square them, add them up, divide by n minus 2, and you get this beautiful thing that is notated as sigma hat e. All this is the typical error of our model. Which makes perfect sense. The residual is a kind of error, and we have different sizes of residuals. So what is the average residual in a sense? What's the average error? What's the average performance of our model? Well, it's this thing that is called by many names. And in my guide for interpreting R output, you will see all the different names for it. The book calls this regression standard error. R calls it residual standard error. But all this thing is, this sigma hat E, is just saying how well my model does at predicting the data on average. It's the regression standard error or the residual standard error. I just like to think of it as the typical error. And we want it small. So for example, if I just say that the residual standard error for this fake situation with housing data is, say, $5,000. What that's telling me is that my model, on average, is about $5,000 off when it tries to predict each of these data points. You could think of it as, on average, the residual is $5,000. It's not technically that because of the math, but in how we talk about it, that's just fine. There goes my marker. So that's all this is. And it's in the R output. It's in the help guide for the R output. And it's talked about in chapter 1. But again, it's a very simple assessment for how close or far away does my model get in predicting my observed values. So I'll refer to this thing a lot, and you can just keep that in the back of your mind going forward. Okay, last thing, assumptions. Regression doesn't work unless we meet certain assumptions. If assumptions are not met, then our results are not reliable. It's as simple as that. So what assumptions must we meet in order to use regression? Well, the book sort of talks about 4. It might talk about a couple others. We're going to focus on 4, and we're going to always check for assumptions with our modeling situation. And the way we're going to do that is just methodically going through each one, and you'll see how. So what assumptions must our model meet in order for us to use linear regression? Well, there needs to be a linear relationship in the first place. And how can we check that? Well, we use a scatter plot. Just like we have right here. In fact, before I even drew a line on here, we looked at it and said, hey, that looks like it could be linear. So we have the scatter plot to check for that. And if I see curvature, so I'm going to erase this. So if I have data that looks like this, that looks like it's got a big curve to it. I would not use linear regression without making some kind of transformation. We'll talk about transformations in a couple weeks. And they're talked a little bit about in the book in chapter 1, but we're going to hold off on that. So if my scatter plot's curved in any which way, I don't want to just dive into linear regression. I maybe want to try some kind of transformation first. So we want to see a linear pattern on our scatter plot. The second assumption is independence. All independence is saying is that each of our y observations are independent of one another. In other words, for our pricing and square feet example, we want each house price to be independent of every other house price. We don't want the price of one house influencing the price of another house. If it is, then it's introducing dependence between our observations. It's introducing dependence between our housing prices. And that's not accounted for when we do linear regression. So for our purposes, we don't do graphs for checking independence. There are some used in economics and time series data on different situations. We just ask the question logically. Does one observation influence another observation in the response variable? If the answer is no, then we have independence. Now the book, here's one correction from the book. The book says that if you get a random sample, you will have independence. That's not technically true. So that is, I would say, an error in the book. A random sample, you want a random sample at a base minimum anyway, but a random sample does not ensure independence. Because you could take a random sample of twins, for example, and twins are not independent of one another. If you measure the health of one twin, that will very likely be correlated with the health of another twin, and those twin measures are not independent. So just taking a random sample doesn't address all of that. So again, you just ask the question, is my response variable observation here independent or dependent on some other response observation over here? The third assumption to check is normality of errors. In this case, our residuals. So remember, each of our observations had a residual because our model didn't get it exactly right. There's a residual. Well, we can take those residuals and we can graph them and we can see if they're normal or not. And just as a little reminder, let's say I had an example histogram here and just say residuals. I want this to be a nice normal distribution. That's what we want our residuals to be. If they're not normal, that means that our residuals are not great for letting us interpret our model. So if there's any kind of skew, or if that actually was not a lot of skew, something like this. So that's like really skewed. That's a problem. And we don't have to look at a histogram. We can look at a box plot. We can also look at a QQ plot. And I go into that in more detail in the R script video because I show you the graph of that. But there are different ways to check for normality. So what I want you to do with that is check a histogram, a box plot, or a QQ plot. Finally, absolute last thing, we need constant error variance. So again, we take our residuals and we can see how they're distributed, but we can also see how much the residuals vary. Remember, some residuals were closer to the line, some residuals were farther away from the line. And how we do this is, and this is shown in detail in the help and tips video. How we do this is we put the predicted values on the x-axis as our x-axis, and then we use the residuals on the y-axis. And our residuals will be centered around 0. They'll generally be in the middle, ideally. So what we want to see with this graph, we want to see an even spread of our residuals above and below this y equals 0 line, this horizontal line, as we move from left to right along our predicted values. This is what constant error variance looks like. If we don't have constant error variance, what we get is we get patterns. Maybe we get something that looks like this. Maybe for small predicted values, we get residuals that are close to the line. And then the bigger we get in our predicted values, the more spread out our errors become. This is a common problematic shape for our error variance. And we'll see why next week, why this is really important. So this would violate the assumption of constant error variance because it's fanning outward. The error variance is small right here because they're close to the line. And then the errors are a lot bigger and a lot more spread out farther away from the line. So anything that deviates from a nice even spread above and below the line of y equals 0 violates the constant error variance assumption. And I'll just say that in general, you can violate an assumption moderately, one or two of them, and probably still be okay in interpreting your model. If you severely violate, say, constant error variance or severely violate independence, then you run into trouble. So this is where we run into the fuzzy zone of statistics. And as we get into more examples, you'll see where this plays out. But I'm just preparing you to say, there's no clear line to say, oh, you have violated your assumption way too far. and you can't use this model anymore. Some people are more liberal with assumptions, some people are more conservative. But you need to check each of these things, and like on the homework, I don't care if assumptions are violated, I just want you to check them and talk about them. So all that explanation is in the homework when you do that, and with my video about the homework. So if a lot of this didn't make sense yet, that's okay. This is just sort of the first crack at it. Doing the activities and asking questions will help clarify these things. But definitely just keep everything we did in mind, the terminology, the predicted values, the residuals, typical error, the fact that we have to check assumptions. This is really the language we start to use for things, and that we'll keep referring to over and over again going forward. So I hope this was helpful, and definitely, of course, if something's not clear, ask me questions. If I didn't talk about it really in this video, or if it didn't come up in the activity or the challenge sheet, then you don't need to worry about it. I know because the book gets into some other things with outliers and transformations. We'll get to those things when necessary. I'm giving you everything you need, and again, if everything you do on the activities and the challenge sheet gets you set up for the homework, and everything you do on the homework and the activities sets you up for the exams. So think about this stuff. Go back to the book definitely if you need to, and send me questions. So thanks, and have a good week.